Do you feel the vibes?
Okay, I'll stamp your homework in a minute. Okay, so rational functions. So we know what a rational function is. It's basically a function where there is a polynomial divided by another polynomial. And we also know that to find the domain of a rational function, it's basically all real numbers except whatever value makes the denominator 0, right? And because there are points where the denominator can be 0, so the whole function can be undefined, many rational functions will also have asymptotes. Not all of them, but many of them. Okay, so in this lesson, we're going to go through each of the different types of asymptotes, how to find them, and then how to graph rational functions. So let's start with horizontal asymptotes, right? So a horizontal asymptote is a line, y equals c, that basically serves as the end behavior of a graph. Okay? Now, it's basically at what value does the graph flatten out as you approach either positive infinity or negative infinity. Now, officially, the definition of a horizontal asymptote, so we use that to find a horizontal asymptote. The definition is the limit of f of x as x approaches infinity, or the limit of f of x as x approaches negative infinity. Okay? Now, because of that, because it's only at the infinities, suppose this is your f of x, and suppose there is a horizontal asymptote right here. The horizontal asymptote only takes effect at the infinities. That means a graph will have to follow the horizontal asymptote at the infinities, and then in the middle here, it can cross the horizontal asymptote as many times as it likes, and then just follow it at the opposite end. Okay? It only takes effect at the infinities. Quickly.
So basically what you're saying is the infinity is just whatever the end of the graph is, wherever you decide to
Right.
end the graph. So it could end
No.
after the second bump and
No.
the infinity would be
No. Let's just do the whole lesson and then we'll see. Okay, so how do you find horizontal asymptotes? You have to, because it's at the infinities, we only look at the leading term, right? So we take the leading term from the top, the leading term from the bottom. It's just like the leading term test. So if you have a rational function with a higher degree in the denominator, then the horizontal asymptote is y equals 0. So for example, suppose your f of x is, 6x squared plus 3 over 3x to the 4 minus 7. What we have to do is this. The limit of f of x as x approaches infinity. So again, you only take the leading terms, right? So this is the limit as x approaches infinity, 6x squared over 3x to the 4. This is 2 over x squared, right? Hang on. This is the limit as x approaches infinity, 2 over x squared. Now, what happens as x approaches to infinity? What happens to this whole thing? 0. And then if you do the same thing, the limit of f of x as x approaches negative infinity, now this is the limit as x approaches negative infinity, 2 over x squared. And again, if this is negative infinity, the whole thing will still equal 0. So the horizontal asymptote will just be y equals 0. Now, Do we have to do all this every single time? No. It's enough to just look at the highest degree on the top, the highest degree on the bottom, and then you can figure out what your asymptote is. Now, if they have equal degrees, then the horizontal asymptote is the reduced form of the fraction. So, f of x, so suppose, for example, f of x is 6x cubed plus 1, and then, I don't know, 3x cubed minus 1, right? So now the limit of f of x as x approaches infinity, well, it's just going to be this over this. What will that be? Just 2. And same if it's negative infinity. Just, positive 2, right? Just 2. So the horizontal asymptote is y equals 2. You just take the coefficient, and you reduce. Now, if there is a lower degree on the bottom, there is no horizontal asymptote. Okay? That's it. Now, we are going to look at another case later where if the numerator has a higher degree by 1, there is an oblique asymptote, but that still means there is no horizontal asymptote. Those things. So, those are horizontal. Let's go to vertical. Vertical asymptotes. Okay. Vertical asymptote is a line x equals c. And if it's the graph approaching infinity or negative infinity as you approach a value, right? So for example, take a look at this one. This is x equals negative 2. As you approach negative 2 from the left, the graph is going up to the infinities. As you approach negative 2 from the right, the graph is going up to the infinities. So if, as you approach a value, the graph is going up to infinity or down to infinity, that point is a vertical asymptote, or there is a vertical asymptote at that point. So, how do you find vertical asymptotes? First, you have to simplify the function. And then you have to find the zeros of the denominator which couldn't be eliminated. Okay? All right. So let's do a couple of examples. Take a look at this one. We want to find domain, vertical and horizontal asymptotes, and all that other stuff. So, so for the domain, you have to set the denominator equal to 0. Okay? So x squared is 17. X is plus or minus root 17. So it can't exist in those points. That means the domain is negative infinity to negative root 17, negative root 17 to positive root 17, and then root 17 to infinity. That's the domain. Now let's do vertical asymptote. You simply set the denominator equal to 0. X is plus or minus root 17. That's your vertical asymptote. Okay? Lastly, horizontal asymptote. Okay. You have to do the limit of f of x as x approaches infinity. Okay? You have to, because this is how we're going to justify. So you don't have to do the calculation. So here, what is it going to be? 5 over 2. The limit of f of x as x approaches negative infinity, still 5 over 2. So tomorrow I'll go over some examples where they will be different, and you will have 2 horizontal asymptotes. I actually need to write a note because there was something else that I forgot to stress to the other class.
So you have to do the, like, say, the limit?
Yeah. This is how we're going to justify our answers, right? So if I ask you find the, so here, the horizontal asymptote is y equals 5 over 2. If I've asked you to justify your answer, then you have to show me this. But if it's just a list of like, okay, list this, then you don't have to show it if you don't want to. Okay, so that's that. Okay, let me do another one and then I'll pause for questions. This one, domain. Set the denominator equal to 0. X squared is, x squared is negative a half. Is that possible? No. What that means is there are no real values for which the denominator is 0. Well, if no value makes the denominator 0, then we have no problem. The domain is all real numbers. Okay? So just because it's a rational function, it doesn't mean that it's got to have some discontinuity somewhere. So what's the vertical asymptote then? None. And on a test or a quiz, if there's a slot for vertical asymptote, don't leave it blank. Write out none. Okay. Horizontal asymptote. So this is the limit of f of x as x approaches infinity. And what will it be? 2. The limit of f of x as x approaches negative infinity. Also 2, so y equals 2. You must say y equals and x equals. Okay, quick questions. Yeah.
So we have to show limits, but we don't have to, like, we can just do it short to know that it's 2. We don't have to do any other.
Correct. Yeah. Okay, right, Evan and then Justin.
On the last page, the horizontal asymptote for A, when you're finding, you have to simplify the fraction. Are you just taking into account the first thing?
Yeah, leading term.
And then also on this one?
Also on this one, leading term.
The asymptote, the reason why it's 9 is because it's imaginary.
Yeah. Okay, this one. Oh, sorry.
When you write the design test, when you write the asymptote, you want us to write it
No. We'll do that in chapter 12. Okay, this one.
Like, how are we writing it? It's not like that.
Doesn't matter.
So you
Just say x equals whatever. Yeah. You don't have to put limit notation. Okay. So here we go. Domain, right? So 2x minus 34 equals 0. X is 17. So negative infinity to 17. 17 to infinity. That's my domain. What's the vertical asymptote? X equals 17, you mean? That's right. Okay, horizontal asymptote. Limit of, okay, so hang on. Limit of g of x as x approaches infinity. This will be the limit as x approaches infinity. 6x squared over 2x, which will be how much? 3x. So as x approaches infinity, what will this be? Well, yes, but as x approaches infinity, it'll be 3 times infinity, which is infinity. So it can't, because it's not flattening out at a finite number, that's the reason why if there's a higher degree in the numerator, it is not a horizontal asymptote, right? A horizontal asymptote, it has to flatten out at a finite number as x approaches infinity. It's in the limit is infinity, which means there is no horizontal asymptote.
But do we have to say a weak asymptote?
No, what not right. Right now I'm asking you, is there a horizontal asymptote? And it's simply no. Yeah.
For the, or actually, or I can get this question when we go to.
Okay. So this one can be factored. So you factor it. Okay. Okay, so for the domain, negative infinity to negative 4, negative 4 to 2, 2 to infinity. What's the vertical asymptote? What do you guys think? X equals 2, x equals negative 4. Okay, for the horizontal asymptote, look at original function. Okay, so what is it? Y equals what? 0. Y equals 0 because lower degree on top. Lower degree on top. Yes, lower degree on top, higher on the bottom. Fabulous. All right, good.
Do we have to show the
Now let's graph, only if it says justify. Now let's graph a couple.
Oh,
Yeah.
Is that how, like, on a quiz or test you want to, like, make sure you get the
I mean, this one's different because it's asking you for 3 different things. So I just like did it that way. Okay, so first we factor. Okay, let's state domain. Okay, I think we are experts at this by now. Okay, what are the vertical asymptotes? 2 and negative 2. So you can write x equals plus or minus 2. What's the horizontal asymptote? Y equals 0. Okay. Vertical asymptote. Okay, so at 0, we have a horizontal asymptote. 2, negative 2. What else? Now we have to graph. All right. It's also important to find the zeros. For the zeros, you have to set the numerator equal to 0. So here it's x plus 1 equal to 0, x equals negative 1. Okay. So we have 3 regions, right? We know that at the very ends, it has to follow the horizontal asymptote. So let's see how it looks in the middle here. Why don't we test some points? Right? Let's do some test points. Okay, x equals 0 is always a valuable number because that's the y-intercept. So when x is 0, what's y? Negative 1/4. So now we know it's got to cross and, these 2 points. And then to the left, it has to follow a vertical asymptote. To the right, it has to follow a vertical asymptote. So there's really one way for this to look because there is only one 0, and that's this. Okay? Okay, so now the rest of the parts. You could again plug in test points, but take a look. This is like one of those video games, right? The video games where like the character exits the screen from one side and then re-enters from the other side. Yes. So if it exits from the bottom here to the right, to the left of the asymptote, it has to re-enter at the top to the right. So no other zeros. So it's not allowed to cross. That means it comes down and then it's got to follow this asymptote right there. On the opposite side, it left the screen to the top. It exited at the top. It's going to re-enter at the bottom and follow here. No other zeros. You are not allowed to cross the x-axis anymore. That is so much fun. I know. So, it's like a whole party. Notice, at the asymptotes, the graph changed signs. Here, the graph was negative, but then when re-entered, the graph is positive. Y is positive. Here, y is positive, but on the other side of the asymptote, y is negative. Huh? It's Descartes' rule. It's also
Wait, how did you know that?
it's also like multiplicities. Okay, more to follow. Let's do number 2.
Can I have like a private?
Okay, why don't we do the second one? Okay, let's do the second one. Let's factor first because everything comes from factoring. What is this? That's right. 2x minus 2 squared. So domain, we just can't have a 2, so negative infinity to 2, 2 to infinity. What's the vertical asymptote? X equals 2. Horizontal asymptote? So it's going to be, okay,
1/2.
1/2, right? Because we have x squared and 2x squared, so it's 1/2. So if you wanted to show that x squared over 2x squared, it'll be 1/2. So y equals 1/2. Okay, what are the zeros? X plus 3, x minus 4 equal to 0. Negative 3 and 4. Okay, let's put our horizontal asymptote at y equals 1/2. Vertical asymptote at x equals 2. Okay, let's test some points. So x, y, when x is 0, how much is y? Negative 12 over 2 times 4. So how much is that? Negative 3 over 2. Here we go. Right? Okay. So that means on the left-hand side, graph is going to come over this way, hit, and come off here. Okay. Okay, guys, take a look. Remember how if there is a 0 at this point, right? And the graph comes over this way. If there is a multiplicity of 2, what happens to the graph? It bounces back off. So if it's positive, it stays positive. So let's come over here for a minute. Where did we get this asymptote from, the x equals 2? From here. What's the multiplicity there? It's an even multiplicity, so it can't change sign over there. It's got to re-enter from here. It's got to hit that 0, but then follow the asymptote. So come up here, hit the 0, follow the asymptote. That's how it looks. Do you see where multiplicities also take effect? So at the asymptote, the graph will change sign if there is an odd multiplicity. If there is an even multiplicity, the graph will not change sign. It'll stay on the same side of the x-axis. That is so cool. Okay, yes, question. Hang on.
So I don't understand why the multiplicity is involved here if it's not it's
Right, because it doesn't only, multiplicities are not unique to zeros.
But when because it's an asymptote, when does it stay the same?
If it's an even multiplicity, because look, if I have 3 minus 2 on this side, squared, it's positive. If I have 1 minus 2 squared on this side, it's still positive here, right? At this asymptote, at x minus 2 squared right here, at x minus 2 squared, whether I put in a number to the left of 2 or to the right of 2, the sign does not change. But here it's different. If I put in a number to the left of 2 and to the right of 2, they'll be different.
Okay,
Like
so
here.
the behavior is
Yeah.
it's just not different.
Yep. Okay.
What is blue part mean?
Okay, we are not talking about that right now. Okay. Okay. So oblique asymptotes. So we did horizontal, we did vertical, let's do oblique. An oblique asymptote is in the form of a linear function, y equals mx plus b, if the numerator has a higher degree by 1. To find the oblique asymptote, divide, then take the quotient. Okay? You throw away the remainder. So let's do one here. This one doesn't factor. So let's find the domain. Negative infinity to negative 3. Negative 3 to infinity. Vertical asymptote, x equals negative 3. What about horizontal asymptote? None. Now, for the oblique, here's what you got to do. You have to do either synthetic or long division. In this case, we can do synthetic, so let's do synthetic. So negative 3, 1, 1, negative 8. 1, negative 3, negative 2, 6, negative 2. That remainder gets tossed out. We don't need it. This depressed polynomial is x minus 2, right? So the oblique asymptote is y equals x minus 2. Okay, let's graph this thing. Y equals x minus 2 looks like this. Right? I'm just putting some extra points so it's more precise. Use a ruler if you have to. Where is the vertical asymptote? Negative 3. I love math. Okay? All right, let's graph. Zeros. So we don't have a calculator. Okay? The 0 here can't be factored, so it's probably, it's irrational zeros. Right? You can do it by the quadratic formula. So you're going to have like plus or minus 2 zeros. Fine. Okay, no information there because I don't have a calculator and I really can't, even if I found the expression, I couldn't compute the value of it, the decimal value. Okay, so why don't we do some points then? X is 0. What's y? Negative 8 over 3, which is negative 2 point something, right? Here. Is that right? Okay, let's put in another point. Why don't I put in something closer to the asymptote? Okay, let me do negative 2. You know why negative 2? Because the denominator will be 1. So what do you have in the numerator then? 4 minus 2 minus 8. How much is that? Negative 6. So at negative 2, it's negative 6. Okay, that's shaping out nicely. Because here I need to follow the vertical asymptote. And then here, the oblique asymptote. So the 0 is probably somewhere over here. So I graph. And no one's stopping you from putting in an additional point somewhere. Right? Put in like x equals 3 if you want. Whatever. Okay, now, look at this vertical asymptote. It came from x plus 3. What's the multiplicity? 1. That means it's got to re-enter from here. Isn't that awesome? And then there has to be another 0 here. So it's going to come and there. Now, if you want, why don't we put in another 0? Why don't we put in negative 4? I'm sorry, another point, negative 4. What do we get when we put in negative 4? You get negative 1 at the bottom. So 16 minus 4 minus 8. How much is that? 12 minus negative 4. Oh my God, look. Oh my God, that was like perfect. It's actually right there. Isn't that cool? Like that's like the coolest thing ever. Come on. Right? Oh boy. Oh my gosh. Thank you, Aiden. You're really carrying this 1/3 of the Aidens like pretty well. Okay, yeah.
2/3.
Well, only 1/3 of them clapped. Okay.
So is there a reason why, like, in the weak asymptotes, like, there are no points and there is no graph there?
Huh?
Sorry, that was really poorly. Like, at, like, x equals -2 and whatnot, like, all of that space, like, there's no graph.
Are you sure?
No, that's what I'm saying.
Here.
No, sorry, that's not what I meant. I meant, like, yeah.
Okay, you can't put another point here because then it won't be a function.
Right.
Yeah? It has to pass the vertical line test. Yeah, make sure it's a function. See, math. It's gonna get you. It got to follow the rules. Yeah.
Is there a different type of asymptote we don't know about?
No, this is it. This is it.
Even if the degree is like
Yeah.
2 higher?
No, that's it. Because then it'll just be infinity. You can't divide that.
Okay, so if the degree is like higher by 2 or more, then it's just
Yeah, because
no
when you
asymptote.
divide that, you'll get a parabola as a quotient, right? You'll get like x squared, a quadratic function as a quotient, and you
So
can't
no
have a.
asymptote.
Okay, removable discontinuities. Okay, so removable discontinuities happen when there is a common term in the numerator and denominator which can be eliminated. So let's factor this. And here we have what? X minus 3, x plus 2. The x minus 3's cancel, so we are left with x plus 3 over x plus 2. Now, domain. All of the discontinuities of the original function must be represented in the domain. So both the 3 and the -2. So negative infinity to -2, -2 to 3, 3 to infinity. What's the vertical asymptote?
Oh yeah, you mixed up -2 and 3. It's -3 and 2.
No.
Oh wait, no, never mind.
Wait, we factored correctly.
But they're both positives. I don't understand why one of them is negative.
I looked up.
Right here. The denominator. The denominator is 0 at -2 and +3. No.
But the denominator still has.
Guys, listen. All of the discontinuities, all of the points where the denominator is 0 must be represented in your domain. So, this function is undefined at 3 and -2, so the domain can't include those 2 points. Where is the vertical asymptote? X equals -2 only.
Horizontal is that how
Horizontal, y equals 1. Remember, you look at the original function. Okay. Removable discontinuity at x equals 3. Now, I cannot stress this enough. The function is undefined at both of these points. At one of them, there is an infinite discontinuity, a vertical asymptote. At one of them, there is a removable discontinuity. But the function is undefined at both of those points. So both of those points have to show up in the domain, right? And whatever values are excluded from the domain, -2 and 3, they have to show up again as either a vertical asymptote or a removable discontinuity. None of them can be unaccounted for. Yes? Cool. Okay, fabulous. Okay. That's what I forgot to stress to the other class. Okay, so what are the zeros here?
Zeros are
Just -3.
why not -2?
Because
Oh, it's the numerator.
that's right. And you only set the numerator of the reduced function equal to 0. Oh boy. Okay. So let's put some of these things in here. -3. Vertical asymptote is at -2. Where's the horizontal asymptote? 1. Fabulous. Okay, now, let's do some points here. So when x is 0, what's y? Go to the final function, the reduced function, 3 over 2, right? Okay, now, at x equals 3, there is a removable discontinuity. But how do I know if it's here, 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 here? Like, I don't know where it is. And the function is undefined there. So I can never write y equals this value at that point. But I also have to know where it is. So the way we get around it is, what is the limit at that point? So here's what you can do. For the removable discontinuity, you say the limit as x approaches 3 of f of x. This is the limit as x approaches 3, x plus 3, x plus 2. When you say limit, because limit isn't the value at a point, it's where the graph is approaching, you're free to plug in that point. So now what we're going to do is just plug in the 3. So 3 plus 3 over 3 plus 2, 6 over 5. Okay? So at x equals 3 and 6 over 5, 1 and 1/5 is where the removable discontinuity is. Hang on. So now I know this is going to come this way, hit that point, hit this point, and then follow the asymptote. Okay? Vertical asymptote. Does it come from even or odd multiplicity? Vertical asymptote. Vertical asymptote. Odd. X plus 2 is odd. So it's got to come up from here and there. Okay? Whew. Isn't that cool? That is so cool. Okay, question.
Couldn't we have assumed that the removable discontinuity was right above the asymptote because it had to follow?
Nope, because you can cross the horizontal asymptote. So it could have been here. And then it can sometimes like go back up like.
But it wouldn't have been like crazy all over. It had to have been near.
Yeah, near. Yes, but not, it doesn't have to, but it can.
But then why have we never seen that so far?
Press start.